Buenos días a todos.
Good morning, everyone. Thank you for having joined us today. So far, I'm Carlos Martinez. I'm one of the members of LACNIC Soft. I'm the technology manager at LACNIC. Prior to starting with the first tutorial today, I'd like to tell you that several activities are beginning now at the same time. We'll have in room number 6 the tutorial on new trends in secure routing, and in session number 7, the security module of LACNIC. In this room, we'll be starting with the DNS Hackathon, and like Laura was saying, we'll be here until 11 a.m. 16 UTC. I'd like to ask Nicolas Antonello to please come up. He's a senior manager at Nicolas. So where are you, Nico? So he's Regional Technical Engagement Manager for the LAC region at NICAN. That's Nicolas Antoniello.
Bien en camino. Bueno, bien. Yo mientras les voy a ir contando un poco qué es lo que vamos a hacer con...
So let me tell you what we'll be doing with the DNS Hackathon. In the meantime, the idea then is that over the years, we have organized a series of tutorials and activities related to DNS, which were done following a theoretical methodology, many slides, a lot of terminology, but it always happened that one thing is just to listen to these things and to understand the concepts, but then you go back home, you go back to your country, to your office, and trying to explain these things is not so linear. So going from theory to practice is not so straightforward. So we thought it would be good to have guided tutorials. We came with a computer, we showed terminals, and we ran commands. That was a bit better. Definitely it was a bit better, but it lacks, and it has the same problem. So you see someone else running a command, and the person who's running the command, because that person has done it so often, they do it so naturally, and compared to those who do it for the first time. So following that development process, we said, well, those who might be interested, let's do some hands-on activities. Once Nicolas arrives, and he has the material, so we're going to show you and explain a bit of the background theory, and we'll then be giving you a guide with the commands that you can run in a virtual lab, which is running on the Amazon cloud, where each of those who wish to participate, I recommend doing this in groups of 2s and 3s, so each of those participants will be able to connect to a whole set of virtual machines, which will allow you to set up functionalities and behaviors of DNSs, recursive DNSs, authoritative DNSs, and so on. So with that aim, you have to follow a series of steps. You have to register in a form that we'll be sharing with you in a while. And at the end of the day, today, you'll be receiving an email from me with the access credentials to those virtual machines. So where is Nicolas? He's coming from so far away. Where is he? So let me tell you, if I can remember, some of the activities that we're going to organize. So as I was saying, you have at least three virtual machines in each group. And the activities you'll be doing are, for example, to set up a DNS server, a recursive DNS server. That's the easiest task. What is a recursive DNS? Who remembers? Let's see, hands up. That is the one that will do a query through the internet with a given name. I'm going to ask my recursive server through www.google.com, and it's going to ask the root through .com and then .google.com and a further layer www.google.com. So that is somehow the fundamental function that you require from the DNS as an internet user, namely to discover and use things in the internet. There's a type of DNS server that you need, which is the authoritative DNS server. This is the one that will allow us to host zones. And what was a zone? A zone is a set of records. Those records are where we put the information that we want to expose through the DNS. So the authoritative DNS contains this information and shares this to the recursive DNSs when they receive the query. What else could be relevant?
El autoritativo.
The authoritative DNS has certain security requirements that go beyond those of the recursive DNS. So we'll have a couple of additional activities where we will set up behaviors, for example, something that we call Q&A minimization. This is a recently addition to security in DNS. And the aim is to help those who do the query to the DNS not to disclose additional information than that which is required. And you might know that over the past 8 to 10 years, there is a major concern regarding DNS privacy. So Q&A minimization contributes to that to a great extent. We'll also be configuring, or you will try to configure, signing zones with DNSSEC. So we're going to design zones. The DNSSEC, you might know, is a technique to add digital signatures and then verify certain properties, for example, that the queries done to the registries were not done along the path, along the process. So with that aim, as in any case with digital signatures, we'll have a couple of keys which will allow you to have signatures in the zone, as well as another function in the DNSs, which will be the one that will be verifying this. So that is what we hope to achieve all along this week. So if we can somehow manage to achieve those activities in the course of the week, then on Friday, we'll closing this option. I don't know if we have any prizes, but we'll have some way of recognizing those that did as many of these activities that I'm commenting on. So please give me a couple of seconds, allow me to try and connect. So you have the registration form here on the screen available to register.
Llegó mi colega.
So my colleague has arrived. A big round of applause.
¿Qué van a precisar? Eso no lo comenté, ¿ven? Hay una cosa interesante de eso.
Now, one of the interesting things is that this scheme of laboratories, which Nicolas has worked on for some time, will just offer a browser. You don't need any virtual machines or an SSH client, nothing. You just need a more or less updated browser.
Me dice acá.
Nicolas is telling me that he has no authorization to share the screen.
¿Sí? Está. Está. Yo voy para allá, pero
Hola, buenos días a todos.
So good morning, everyone. I apologize for the delay. I had an issue to organize, but I apologize once again, and good morning, everyone. As Carlos was saying, what you have over here is the link to what we will have in the Hackathon Lab of the DNS.
Lo que les vamos a pedir a los que deseen participar, que accedan ahí.
So please access this link, lacnic41-dns.te-labs.training. Once you access that site, you will only see a form, a registration form. It's a Google form, which will ask you for two things: your name and your email address. So what we will do from now until lunchtime, right, Carlos? We have until 11 a.m. Until today, lunchtime. Until after lunch, we will be receiving requests for participation through this form. So after lunch, we will then close the registration form process, and you will all get in your email, you will then receive all the credentials required for accessing each of your own labs.
En el laboratorio van a encontrar
In the lab, you will find, once you access, you'll find a network diagram. You'll also receive a link for a Git repository containing the entire guide for the hackathon and for the challenge that you will be developing throughout the week. So using the guide containing the tasks you have to carry out and the access to the lab, you will then be able to have two recursive servers that you will have to configure in order to have an authoritative server, a primary authoritative server, and two secondary ones, which are the public servers, which will then allow you to configure your own zones. And in the hackathon guide, in the guide containing all the tasks that you have to carry out, they will be explaining the format and the domain assigned to it to configure the authoritative server, as well as some configuration rules and steps that you will have to follow. Finally, you'll have configured an occult authoritative sector containing a bind to public authoritative servers, one with a bind and one with an LXD, he thinks, another email server that will be, if you configure a secondary server, two recursive, a bind and one unbound. You have to sign the zones in the authoritative server. You have to transfer that to us so that we can enter that in the pad of the laboratory zone, which is the authoritative server for this lab for lacnic41dns.te-labs.training, and then configure a whole set of other DNS features regarding security, privacy, and some optimization that we'll be explaining with Carlos. But let me show you, this is the link to the registration form so that you can start with the process. So once again, after lunch, we'll be closing the registration forms, and those who have registered will be receiving their credentials as well as the links to access this, and then you will be able to start with the practice. And the idea is to do this throughout the week, so whenever you can, whenever you wish, you'll have the entire week to develop the hackathon. And by the end of the week, we'll have a brief session where we'll be recognizing all those who were able to develop and achieve some of the tasks. You don't need to achieve every single task. You will see that this has been subdivided into two main groups. First, the configuration for the recursive servers, and then for the authoritative server. And each of these groups, each of these parts, has smaller tasks, 2 or 3 tasks, typically 2 tasks and an additional task. The idea is that you can go as far as you can with completing all the tasks. But once again, it's no requirement to complete every single task. You will do so as you go along. Carlos and myself, and probably Hugo, who I don't know whether he's here, Hugo Salgado, will be lending us a hand, as well as some other colleagues. So if you have any questions during the week, there is a Discord channel for the hackathon specifically. I will be sending you the invitation to the Discord channel containing all the data. Once we give you the information to access the lab, you'll also receive this so that you can make any query, and then we'll be around in the corridors. If you have any questions, or if you get stuck in any of the stages, if you don't know how to configure something because you never did so, so we can help you out in order to advance.
So that's what we'll do for the hackathon challenge. So right now, let's review some of the DNS terms with Carlos. I'm going to click on this link. I'm going to take it away from screen. I will bring it back later on. Let me go back to the first slide of the presentation, and we'll do a very quick review of DNS, Carlos, and you just jump in whenever you want. Let me just have some water.
Nico es famoso por los dichos que tiene, por ejemplo, ese dicho.
Nico is very well known for his sayings. Well, sayings for those of you who speak Spanish. I'm not sure how I would say that in Portuguese. I should find out. Anyway, a very quick review of DNS. I'm sure most of you are familiar, but it's always good to review it. So internet devices, as we all know, will be identified by numbers, identifiers, IP addresses, IPv4, IPv6. When internet was being invented, just as it happened with conventional telephone, someone realized that human beings will memorize, in general, more easily, sequences of words rather than numbers. That's why we have the phone book. The phone book will associate the name of a person with a phone number. So instead of remembering all phone numbers, you can remember the name of that person. Using the phone book, you can access them and reach their phone number to reach out, to call them, or to connect between two phones, two devices, data exchange between those two devices. Similarly, for the internet, someone developed a mechanism that we call DNS, or domain name system, associating names to numbers. Which names? Names of internet services known as domain names. What numbers? Well, those are the IP addresses. Basically, that's the main role for the DNS. Why it was conceived, associating domain names to IP addresses. In a way that if I want to access an internet service, I don't need to remember the IP address because I have the DNS system that will translate it. Initially, the DNS was implemented with a text file. Well, before a text file, it was implemented with a node. Well, John Postal had a node, the block, where he would write down all the hosts from all computers in the early years of the internet that were connected, and the domain name being assigned, and that evolved to a text file that we needed to save in the different devices, the well-known host.txt. And we know how the history goes. The internet went from just a few computers connected at some universities in the US to being what we have today. Of course, a system with a file where we need to transfer to all devices would not be manageable, it would not be possible. A software that has many problems that we'll know, and we won't go into this very much in detail, but that led to generating all these standards that make up what we today know as the DNS, the domain name system. Very quickly, let's look at the main features of the DNS. From an architecture standpoint, the DNS looks like this. This is an inverted tree. It is a hierarchy system, it's not a flat system design. So it is easy or optimal and to have a very quick information search within this very large database. DNS is a very large database that is distributed in two ways. Spatial distribution, that means that data is not concentrated in a single server, but rather scattered around different services around the world. There's no single server that holds all data. We don't have copies of all data, but as we all know, DNS servers, or the information that we have under the DNS service, is scattered around thousands of authoritative servers around the world. They each hold a piece of the entire DNS system. So that decentralization, if you may, that spatial decentralization of the DNS as to where we store information. Another distribution under the DNS or decentralization is what we would call an administrative decentralization. It is distributed, data is distributed around the world, and management is not concentrated either. There's no single organization that manages all data under the DNS, but rather management is also distributed and delegated through a delegation process to different organizations, also organizations of different nature around the world, including individual people. Any of us could actually obtain a domain name, have been delegated the authoritative server, and we now will manage it. I will be a delegate, and I will run, if you may, that management of particular servers for my domain and the information that is there included. That division or that distribution under the DNS is what we call zone. Zone is an administrative distribution. It's a set of domain names, a domain that is managed by one single entity, by the same entity. So that would be what we see here. That zone, what we see to the left, what you see in the dotted line, well, the dotted lines are different domain zones. So that's the definition of this main concept. Domain name, the most formal or technically, is the tag. The tag that we will use for a node. A domain, which is not the same as a domain name. A domain is a node, any node, under the DNS tree, and the entire tree after that node. To the right, we'll see that is being represented under the blue line. Under the blue line, we can see the COM domain, the COM node, and the entire tree below. The name, the domain name, and the entire domain below. And then To the right, we see the zone concept that we've mentioned already, that administrative distribution of domain name systems. So that is what DNS means and what's the architecture like. What kind of information do we store? We can store different types of information. Actually, today we have over 87 different registries, even more probably under the DNS. What are DNS registries? These are the containers where we store information under the DNS. There's a container, a different container for every different type of information that I want to store. Those are the registries. So we have a container to store a domain name equivalence with an IPv4, that is the registry A. It will store the equivalence between a domain name and IPv6 address, that is the for A registry, and each registry will represent a different type of information that I can store under the DNS, and there are over 87, as I said before, different types of information that I can store under the DNS. The 7 that we can see on screen are probably the most popular, the basic ones. The first 2, A and AAA, are those that we use to associate a domain name with an IPv4 or an IPv6 address. Those are the most popular DNS registries, and the reason why DNS actually was devised and was designed, associated a domain name to an IP address. Now, domain resolution process, what it is, what's the architecture like, type of data that is stored, how, and now we'll review how we search for information on the DNS. Before that, let me just say and review that there are 2 types of DNS servers, authoritative and recursive. Authoritative servers are the ones that we just mentioned, the ones that will make up that big database. All servers that have information on some domain name on the DNS, all of those servers will make up the set of authoritative servers implementing the DNS database, implementing the DNS. There's another type of servers, we call them recursive, resolvers, and maybe some other names. But basically, recursive servers are browsers. Basically, these servers are designed to search for information. They don't host information. They have memory to memorize the searches that were made, but they are not authoritative servers. They do not host information that it's been configured by default. They receive queries from the DNS clients, search for information on the DNS, and once they find it, in that DNS tree, they retrieve the information and send it back to the client that has requested it. That's the main feature, the main role of recursive servers. Now, as part of the characteristics of recursive servers, let me also say that they have a cache memory. What is cache? That is a space, typically in the RAM memory of the server that is implementing the recursive server, and every time that the recursive server is searching for something, it is asking something to our authoritative server, searching for information. All of those queries, all that information that the recursive server receives will store in memory for a while, and the main feature of storing that information in the memory is that if there is another client that will search for that same question, or a question that continues in that search sequence, information that the recursive server has already searched for, they don't need to search it again, because they will retrieve it from the memory, optimizing and speeding up the response time in the DNS. If I know it already, I don't need to search for it again. I don't need to ask the authoritative servers again, because I already have it stored in my memory. I retrieve it and I send it to the client. Of course, every time the client stores information in the memory, they won't have it there forever. That's why we have data that is transferred every time an authoritative service responds, a recursive server, as part of the information that is sent. It sends a data field known as TL. That data field tells the authoritative server how, that is the way the authoritative server shows the recursive server for how long that recursive server may store that information in the memory. Once the time is expired, the recursive server will delete it from the memory, won't remember it anymore, and if someone does that search again, they'll have to go look for it again. So why we associate it to a time period? Well, basically what happens if data changes in the authoritative server is someone modifies an association, domain name, IP address, or any registry. If the recursive server, once it was asked, it never searches or asks for that again, there will be no way of updating because the recursive server would never know there's been a change. That's why everything that the recursive server memorizes, it will be stored for a while. After that while, the query or the search needs to be done again.
Let me add something regarding the cache. Some people view this as a nuisance because there are a series of configurations that you have to do related to cache. Now, do a mental calculation. Each recursive hop has a round trip of 50 milliseconds. He corrects himself, 100 milliseconds, 50 there and back. So if you do a recursion with a domain at 3 levels and you have no cache, then this is a recursion that might take 250 and 200 milliseconds each time. So a web page, a typical web page, can have 150 to 200 objects, and multiply that. Even though the browsers do many DNS queries in parallel, this would be, if there were no cache, this would be several seconds of waiting time in order to load a page while you're just waiting for the DNS to return the IPs. So obviously nobody wants to have that, and the experience when this happens, because in some misconfigurations that might occur, that's very bad. That is why the cache eliminates this problem. With the recursions, there's a lot of information that is cacheable and can be repeated. So in practice, we tend to ignore, when we do a web page, we tend to ignore the DNS and DNS times because the cache is very efficient. So we view the cache, somehow this is like a necessary evil, which we have to coexist with. So thank you, Carlos. It's interesting for you to comment many of these details. So this is a typical scheme. This slide must be about 100 years old. Well, maybe not that much, but it's a typical scheme that you might have a client doing a DNS query to a recursive server. The recursive server looks up the information in different authoritative servers, first in the root when they don't have the information, and then it follows a tree through the correct branch until it reaches a node containing the information. That node responds to the recursive server with the information requested, and then this information is returned to the client, or some kind of error message if the information is not available, or if there was any other issue when looking up for this information or with the information as such. So here you see that feature that Carlos was referring to of the recursive server cache. And here we can also refer to some of the details. This example shows a browser. So that is when I write a URL to download a web page in the browser. And to download that web page, I first need to have the IP address of the web server. So that is where the DNS query begins. Once the client receives the IP address of the web server, once the browser obtains that IP address in response to the DNS query, then the DNS part finishes, and then the part begins where the browser downloads a web page. So couple of considerations in this context. The browser doesn't directly send the query to the recursive server. The browser normally sends this DNS query or any app that is executing this to what we call a recursive stub. It's a local recursive server that is running as part of this things that are working in the OS of that device. So that recursive server that only has a basic function, which is to receive the DNS query from all the applications that are running. It receives these and sends this to the recursive server that one has configured. So how is this configured? Most of you already know, of course, but just to review, the most common case for residential users is that the ISP shows what IP address is assigned to the client to connect to internet and to be part of the internet. It also states what are the recursive servers that are available so that the client can use this. Now, it normally happens that residential users are not manually configuring the recursive server. We just trust our ISP. And if we trust our ISP, we don't need to do anything at all. And through different mechanisms, automatic configuration mechanisms,
servidores recursivos, y así es.
and that is how the client obtains the IP addresses from the recursive servers to which the DNS queries are sent. This is not just the only way. You can modify this. You can manually configure any recursive server you wish, provided you have access to the recursive server. Later on, we'll be referring to 3 types of recursive servers. But basically, when I say that to access the recursive server, normally those who set up, manage, and maintain recursive servers don't do so openly. They don't make the use available of the recursive server to any internet or user or device. So they only make this available to an ISP that has when in production. This is done only for the clients. How this is done? This is done through different security mechanisms. For example, access list in the DNS itself, or some security between the DNS server and the network, some router or firewall. We don't really recommend firewalls to put between a recursive server unless it has some specific features for DNS servers. I'll explain this later on. So one doesn't want to have an open recursive server. Carlos would like to add something in this context, what they are and why are these a problem. You will recall that when I started, I said that when I stretch out time at the beginning, I spoke about recursive servers. Now, recursive servers are what you need to serve something in the net. So it is strongly based on the root structure, tree structure that the DNS server has. So initially, one might think that recursive servers could receive queries from anyone. Anyone could ask recursive services from any recursive server. Now, the second question is that all right? Is that a good idea? Now, the problem with that is that it's not such a good idea. Why? Because DNS transport is strongly addressed at the UDP. What are the properties of the UDP? Or what properties does it not have? It's not addressed at connection because it's not connection addressed. It's very easy to do spoofing of the origin and to redirect traffic to a destination that is not the real destination, it's not the real origin. So any server, when they receive a spoof packet, it responds to the address, the origin address. If it is not the correct one, it responds to another address. So this is used as an attack vector. Added to that, we have a situation which is the event of amplification. The DNS has a property, not only the DNS, but many protocols have the property that if they receive a small packet with just a couple of bytes, 50 to 100 bytes, and the answers are thousands of bytes, there is an amplification process there. And this is because that is the way protocols work. You have a question through www.google.com, and then you receive many things that have to do with the way the queries are answered. So you can do a query with spoofing to a recursive server that will then amplify these. So you'll have a kind of amplification of the internet attacks. So you send in a 1 megabit per second flow and you receive an attack of 100 or 500 megabits per second. So it's not only concealing the origin of the attack because there is spoofing, but also in addition to that, it is affecting the bandwidth. So this is something that is quite harmful, and in recent years we have had attacks such as these are called volumetric attacks, and traffic sizes 30 gigabytes per second or 50 gigabytes per second, and these are very difficult to mitigate. So let us not have open recursive DNSs. The open recursive DNSs are the ideal tools for attackers to do amplification attacks. Now, to tell the truth, the large amount of open DNSs, in recent times, the main source of recursive open DNSs are not DNS recursive servers that are intentionally installed, because people already learned that this is a bad idea. Now, the main origin of the open recursive DNSs are the CPEs. These are the routers in the home that have kind of DNS server and are presented to the client's network as a local DNS, and to open a local cache, and so that this is more efficient. But they listen to the external interface, and very often they are open recursive DNSs with unsecure configurations, and sometimes these are not verified prior to installing these on the customer side. So in addition to that, there are many CPEs than the recursive servers. DNS servers are tens of thousands and CPEs are millions. So it's quite a serious problem, that of the open recursive servers. But the main source of open recursive servers are not the ones one would imagine. There are other protocols that could be used for amplification purposes, but this is not an issue of DNS. For example, NTP is a typical one, and having NTP servers that are open to the world is equally bad. So this was to review how the domain name system works and some of the things that we mentioned together with Carlos. Now, it turns out that the domain system in its initial versions contained a whole series of aspects that today could be a potential problem and a concern. For example, security, privacy issues that had not been taken into account in the standards, and they were directly not implemented in the DNS. This is because if we go back in time and in the history of the internet to the initial times, many things work thanks to the goodwill of all those who make their contribution in terms of operations of some or many networks. The network of networks, all those who manage a network that is part of the internet, collaborate in the administration and the proper functioning of the internet. So as part of that goodwill, particularly at the beginning, there were not many players or actors who had the intention of carrying out cyber attacks or that would pose a security threat or a threat to the data privacy. Of course, this is not exclusive of the DNS, but this is a problem that has to do with the entire technology. So that functionality, those features of privacy, security, and optimization started to be added over time, over the history of the internet. Protocols started to be added to the DNS protocol that are part of all the protocols that have to do with the domain name system. I don't really recall how many there are, but more than 150 standards, 150 different RFCs that have to do with all the protocols involving the specification and how the domain system works, or some protocol or functionality that was added. Allow me to tell you an anecdote that impressed me quite a lot. There was someone from Holland who was called Hubert, and he brought together all the RFCs that had to do with DNS, and he identified 2,000 pages of documentation related to DNS. And he called it the DNS Camel. This is available online. He tried to do a sort of a compendium of all the RFCs so that they were all together and grouped with some level of consistency, because what he had identified, and he was quite correct about this, that after 40 years, DNS standards became difficult to follow up. So I were to open up things and say, well, I'm going to program a DNS server. It's very difficult to start to learn and see where I can start reading documents about this. And this is an issue. It's a problem because many of us depend on many implementations and different implementations. So the work done, sometimes the contributions that the world of the internet needs are quite different than what we could think of. And this one of bringing together all the documentation, I think, was quite amazing. So I wanted to share this with you. It's called the DNS Camel. Yes, I recall having seen a kind of dependencies and a sketch explaining this, and it's quite impressive. So if you look at it, it's like a spider web, and the interdependence with all the RFCs and all the standards at the IETF that have to do with the DNS, like Carlos was saying.
So that's one of the aspects that make it more difficult to have one person that knows of all the protocols and domain name system and associated aspects. As I was saying, a number of enhancement, aggregate, or optimizations to a DNS and its environment or ecosystem will add different features. Some to optimize, to make searches quicker, to have a safer system, not safer, to optimize, to accelerate searches, and to have a more resilient system that is more tolerant to failures. Or to reduce the possibility, and that is associated to security and safety, for someone to capture a big part of the system and do something, as Carlos said, as an attack vector, using the DNS as a weapon, an attack not to harm the DNS, but to use it as a weapon to attack a third party. And there are other type of attacks against the DNS. So part of that system will stop working, will stop providing services with the repercussions that we all know. Networks don't stop working if the DNS were to shut down, but in practical terms, it would be hard to use the internet if I don't have a DNS. I would say it's impossible nowadays to use the internet without a DNS. It wouldn't be just difficult, it would be impossible, for many technology implementation reasons that make it critical, and for it for the DNS to be up and running. So let's quickly look at some of the system optimizations. Cache, storage, recursive servers. It's something that's existed since the beginning, since the DNS was created. As Carlos said, the purpose of cache for a recursive server is to accelerate searches and reduce network traffic and the load for authoritative servers, making the system more resilient as it releases authoritative servers to address other queries. If we didn't have a cache, recursive servers would be constantly querying authoritative servers. That's correct. How many copies of routes do we have? Right, you can see the map. Each implementation of the node, a mechanism that we can implement to enhance resilience, if you may, and distribute the load or the burden, is to generate copies of an authoritative server. Each node of the DNS tree might be implemented not just with one server. That's actually a bad practice to implement one single authoritative server for a domain or a zone. Best practices say that we should have a few, at least, authoritative services before mentioning copies. Why should we have a few copies? For several reasons. Some of the most obvious is that we need to update servers. We need to use security patches, we need to change memories, we need to change processors, or they might fail. They might lose connectivity to the network and so on. If I only have one authoritative service for one zone and something happens to that service, or I need to maintain it, or I need to update the DNS servers up, I need to shut it down, I need to disable the DNS service, update the software, and restart the service. So during that time, the server will not be available. If I have only one, the internet will not have the possibility to resolve that zone. So how do we resolve that? Well, having at least two. If something happens to one, I have the second one as a backup. In that scenario, it should take on the entire load for a while, at least until I solve my problem with that other copy, and once resolved, I will have both up and running again. So that would be the minimum redundancy, having two copies. How many copies can I have? As many as I want. Usually, having copies of an authoritative server, the most used recommended practice, there's no single practice, there are many, but the most popular is using the Anycast technique. Using the Anycast technique, I can manage the same IP address with two different servers on any network. Now, what do we need to have for that to be possible so I can assign the same IP address? Well, all servers that have the same IP address need to provide the same service. First of all, they all need to provide the same service. They all need to be DNS authoritative servers and have the exact information. Same service, same information. It doesn't matter if there's more than one service with the same IP address, because it doesn't matter which one I query, they all have the same information. So I will have the same responses regardless of which one I query. If I don't meet those two conditions, the Anycast technique will not work for copies. So the DNS has already protocols to synchronize the information from one zone to one server associated to other copies of that same servers. There's a zone transference that is also part of the DNS protocol, known as the acronym XFR. Is a zone transfer protocol for DNS that allows us to synchronize authoritative servers, and those who will take part on the hackathon lab practice, you will have to implement between the primary authoritative server and the secondary ones. You will have to enable the XFR protocol on the secondary one, so we can retrieve the zone and synchronize with the primary. So you only can set up the primary authoritative servers, and the secondary servers will be synchronized automatically. Every time there is a change on the primary server, the protocol will inform the secondary one. So the protocol already considers all or most cases for synchronization to happen seamlessly and automatically without the need to copy the information to all of the copies. If we look at the root, as Carlos said, we said that each node using any cast, we can have several copies. Now, just let's look at the DNS root. Let's just look at the highest level node, the one that is represented with a dot. That DNS root, how many copies are there online of the DNS root? Why is it important that we do have those copies? It is the most critical node on the DNS tree. Any node, because of the characteristics of the trees, due to the characteristics, architecture characteristics of the tree, if a node stops working, the entire tree below will disappear. It stops working as well. One of the main characteristics of a tree is that there's only one way to get from the root to any node. So if that node disappears, everything below or all the children of that node will not be available either. So the root is the highest node where the DNS hierarchy starts. So if that stops working, we don't have DNS anymore. So how many copies are there? There is an online site that I think it's rootservers.org, root-servers.org. We'll have a list, a map, a world map with a very updated distribution. I mean, there might be a difference of just a few. A list of all copies of the DNS root. That is just for the DNS root. On the map, you'll see on that side those circles. I mean, I know that you cannot see it from where you're seated, but if you access that address, you'll see these orange, green, or yellow circles and a number in the middle. That number says how many copies of root servers there are in that zone. They all have the same information, the information for the DNS root. I did not update that screen grab, but there are over 800 copies worldwide. So there are over 1,800 servers around the world, all responding to the zone root. They all have the exact same information. So that reduces significantly the likelihood of the DNS root not being available at all. And I always like to mention this, Carlos. I think it is remarkable. I think it's incredible. Most of us here today, I didn't ask, but I'm sure that all of us who are technical experts and work at an operation centers or have worked at any point and work with networks, we know that everything fails at some point. We don't ask ourselves if it's going to fail. We just ask when it's going to fail. We hope that doesn't happen. So if you're asking yourself, is it going to fail? Just move on to the next question, because everything fails. The question is when, and of course, to be as few times as possible. Now, the DNS itself, as a global service, as a global application, at the root level, it had no failures, not a single failure since it was invented, maybe 40 years ago, over 40 years ago. I'm not familiar. Well, maybe the GPS system has failed at some point, but I really do not know of any cases. When it comes to data networks, the data networks that we're all familiar with, I don't know any other cases. Maybe one, maybe I can just think of GPS system. It's interesting what you're saying. It doesn't mean that individually each one of these servers hasn't failed, but we're speaking about the system as a whole. 2001 volumetric attack came close, and that's what helped us identify the problem and push the community to deploy ethnic copies of the root servers. So LACNIC has a program that's called More Roots, where we fund the more root copies across Latin America, and we have funded over 30 copies. We have acted as a sort of broker between operators and associations in the region. So you can read about the Más Raíces program on our website, and maybe you can join and also contribute to that program. Out of the 1,900 copies, there are over 30 that were set up as a product of that LACNIC program. The program is called Más Raíces, plus Raíces. So using this program, we can replicate root services, and using the NECAS technique, we can replicate any server. Our own authoritative servers, not just the root, anywhere in the DNS tree. If I operate an authoritative server using the NECAS technique and the zone transfer protocols that you will use, if you take part in this week's hackathon, you can also have replicas or copies or your authoritative servers. You'll see that it's much easier to set up if you're not familiar with this technique or this type of setup. You'll see how easy it is. I mean, we sometimes are afraid that it's something hard to manage or implement. It's not hard to implement, not hard to manage. You just have to do it and, of course, become familiar. It's not trivial either, but it's not hard. It's something that any of us here can do if you are used to working with online servers and operating networks at the ISP level, and it's something that we can all easily do, and probably is the best mechanism for enhancing resilience and its low implementation costs. About any cast, it's used for roots, but you can use it for any DNS server. It's actually a great practice, even for recursive to small operators, because it's easy to do. I want to do an Anycast tutorial, a very short tutorial. I've been working with Anycast DNS. I have 2 small servers at home and a microtrick, and I do Anycast just with that at home. And I resolved a problem that whenever I travel and something broke down at home, that just solved the problem. At the hackathon, we can also access the router. If you're taking part in the hackathon, the access to router is disabled for your own routes, but we could add that practice implementing Anycast for primary servers and authoritative and recursive as well.
Yes, Anycast can also be implemented for recursive servers. You can have multiple copies, and that is even far more practical for the ISPs, because an ISP typically, as a service to its customers, has a recursive server, not an authoritative server. There are ISPs that use authoritative servers for a domain in addition for their own purpose, but publicly almost all ISPs operate their own recursive servers or give their clients an address to use an open recursive server. But yes, all the ISPs tell their clients what recursive servers to use. And the Anycast techniques can be used to replicate recursive servers. It's not just sending 2 recursive servers to my clients, as was done historically, but also these 2 IP addresses or one of the 2 addresses can be used through the Anycast technique to replicate as many times as I wish, and then I can have like a data center with 10 recursive servers that can be virtual servers or other servers, all with the same IP address, all recursive servers, and following the Anycast technique, this will work very well. You also have to have some considerations when you use Anycast in a recursive server because of the persistence of the TCP connections, and this could be an issue, but it can be easily solved. You have to take care with the load balancing that is used in those networks because you have the DNS servers. So what we have here on the screen is like an enormous scheme of the entire DNS ecosystem. And the red crosses are some of those points where the system might be subject to some form of attack or failure or threat. So there are some protocols that have been added to the domain names that try somehow to minimize the impact of these threats, of these attacks and these problems if they occur, or in some cases to solve these. Sometimes the implemented protocols, if you have implemented these, prevent 100% from these things happening. As there's not just one solution to everything. Like Carlos said, there are 2,000 pages and 70 RFCs, which are standards related to the DNS system. So if I wish to implement all the security measures and all the privacy measures, it is likely that I have time to implement all the protocols. But there is a small number of protocols that I can implement and which is secure to implement and have been in operation for quite a number of years and do not pose an operational overload, any major operational overload. Many of these are the protocols that we request you to implement in the course of the hackathon. So let us rapidly refer to some of these and explain where these happen and what are the problems they solve or mitigate and what they are called. So speaking about security, there is a protocol that was designed to apply between the recursive and the authoritative servers. This is called the DNS Sec. It is a security extension to the domain name that adds precisely not the entire security, the DNS security, and it's not all solved with DNS Sec, but it does solve an issue which was what led to design this protocol initially and also contributes to mitigating the likelihood of other cases, other situations. Please, can you explain, Carlos, what the DNSSEC solves and what was the motivation to create this? The origins of the DNSSEC stem from different places. You might recall that I spoke about the UDP, namely that although the DNS can use TCP and UDP in general terms, preference is for UDP because of the speed in the response. So remember the mental calculation I made of some seconds. If you add the TCP handshake, you're adding an additional time. So UDP, because it has no connection, requires, imagine this is a server that receives many queries in UDP packets. You have to distinguish who is sending this query in order to answer this. The same IP address at the same time from the same customer might be making several queries. Well, you might say, well, I can distinguish these easily because of the origin IP address of this UDP packet. But you need something else. You need something that allows you to distinguish between parallel queries from the same client. With that aim, a field was created in the header of the DNS packets, which is called query ID. This is a 16-bit number. This 16-bit number allows the client to identify the query with a unique number which is created at random of 16 bits. So how does a DNS server know what it has to answer? It has the client's IP address, it has a query ID, and it also has a question. The question is part of what you wish to identify. So imagine this as follows. If you could guess those query IDs, those 16-bit numbers, you could do spoofing. Because the origin IP address of the queries, if you're looking at the ISP network, are easy to guess. The IP addresses are in the whois. Or any client can know these and infer which are the IP addresses of a given ISP. So the protection of trying to guess the IP address is relative. If I were to do a blanket attack, if I wish to do a direct attack. But if we wish to do an attack, which are those attacks that it doesn't matter how many victims there are or who, then the origin IP address is very easy to guess. So what is the protection I have? This is a 16-bit number. The 16-bit number, you are aware, maybe back in 1980 this was a reasonable protection, but guessing a 16 number address is not so easy. So theoretically this has been known for quite some time now. Now it turns out that in practice at a Black Hat event back in 2004 or 2005, Dan Kaminsky, a very famous researcher who unfortunately died a couple of years ago. So Kaminsky demonstrated this in practice in an event such as this. He lost his computer and he started running scripts, and he demonstrated this attack that I'm telling you about, namely to be able to somehow deceive the clients and received false DNS responses. So this leads to a certain uncertainty and nervousness, but many people had already been working on strategies to add security to the DNS, but none had really reached very far. So DNSSEC as we have it today should be called DNSSEC version 2. Prior to that, there was an undeployable DNSSEC which introduced too many changes and made this totally unfeasible. So as a result of Kaminsky's attack and that attack family called night cache poisoning, this led to the need of a DNS. Now DNSSEC will allow me to add digital signatures to the responses. The DNSSEC will have a couple of keys, will generate signatures that won't be generated by zone. Some say the zone has been signed. The zones are not signed at the DNSSEC. What you sign are the resource record sets. So this is what is signed. Each has its own signature, and those are ones that are verified. Remember, when we do recursion, you don't ask for the entire zone, you ask for a specific zone. So when we look at it this way, signing the entire zone is pointless. Sometimes we do like an abuse of language when we say that the zone has been signed and all the records of the zone have been signed. Now, what is a DNSSEC protocol? This will allow us to verify that those who are answering are those that should be answering, because the signature shows that those who provide the answer are those who have the private key. So this is what any digital signature indicates. So that is a large share of the benefits of the DNSSEC. DNSSEC doesn't give us something that is confidentiality. DNSSEC does not do traffic encryption. DNSSEC is plain text. There are other techniques to mitigate this that are out of the scope of this tutorial, but maybe in the future we could add this. DNSSEC allows us to verify the integrity and authenticity of the response, but doesn't provide confidentiality. Okay, thank you, Carlos. So DNS adds that security that Carlos was telling us about between the dialogue, between the data exchange between a recursive and authoritative server. And as part of what he was explaining and the motivation, the initial motivation to do this was to solve the cache poisoning attack. Well, it's easy, or it was quite neat, because at that event he triggered all this. People had already been working this when Kaminsky showed this, and there were other similar attacks, but you can imagine the faces of people. He just opened his computer, he ran a couple of things, and that was it. Within a couple of minutes, he was able to demonstrate it in practice, something that was known in theory for some time now, but nobody had really verified how easy it was to do this. Now, I would like to explain that there are other protocols you might have heard of and might know to a greater or lesser extent. But one of these are those that we call sometimes DOX, which are the protocols like that we call DOH and DOT. Protocols that add privacy, not in the case of security, but privacy between the dialogue of the client's device and the recursive server. So what these two protocols do, DOH and DOT. DOH is DNS over HTTPS, and DOT is DNS over TLS. These are two protocols designed in order to encrypt information between a device or a client's app and a server. In this case, if I'm using DOH, I will generate an encrypted channel between the web browser and the recursive DNS server. Obviously, the DNS server, the recursive DNS server, and the one who manages it has to support this protocol, has to support and enable the functionality of DOH so that the clients can use it. It's not just about the client configuring this; it has to be configured on the client side and also on the person in charge of managing the recursive DNS. In the case of DOT, DNS over TLS, the encrypted channel, instead of being generated between the web browser and the recursive server, this is generated between the device or the encryption application of the device and the DNS. Now, the difference is that in some cases, if I have different browsers, I would have to configure or enable DNH in the 5 different browsers, and in the case of TLS, with one encrypted channel between the application that implements the TLS protocol and any recursive server and any other application that I'm implementing on the customer side can use this channel to conduct the DNS queries privately. Now, what is the benefit of encrypting this information between the client and the recursive server is that anyone who can capture this information that travels between the recursive DNS server and the client, if this is encrypted, then it would be impossible to understand and not even the answers to those queries. So I'm concealing these answers from anyone who wishes to try and read this channel. If I don't implement these protocols, anyone who can access the channel, anyone who is participating in the data transmission of the channel could then see which are the DNS queries I'm doing and what are the answers I receive. So basically, knowing the DNS queries that one does, one can know 100% of the online activity of a given device or person. Just because of the queries I do, if I'm doing a query to a health service, it is likely that I'm not doing it just for any reason. Normally, it's because I am sick or there's someone in my family who has a health problem. So if I do an query to access a website of a manufacturer, so based on all that information, quite obviously, we can do directed commercial publicity or many other things. We're all aware today that the power is in the hands of those who have the information and not necessarily in the hands of those who manage the devices or the networks.
So having information or getting information from my clients' online activity is critical nowadays for marketing, for the entire financial ecosystem worldwide, which is all about the internet. Basically, those protocols are conceived for this, for clients to hide DNS information, queries, and responses traveling from their devices to recursive servers. There's a little bit of history that we won't go too much in depth. This queue name minimization protocol, what it does is, first of all, where does it act? Between the recursive server and authoritative server. So the dialogue between those two. We won't review in depth what the sequence for name resolution is like, how the recursive server, well, it asks the different authoritative servers from the root to search and find the information the client wants. In that search for information, if we look at the original DNS standard, recursive DNS servers always send the same full query they received from the client to each recursive authoritative server. Every time a recursive asks an authoritative, it sends the exact same information. If I want to know the IPv4 address associated to www.example.com, the recursive will always ask the same regardless of which authoritative is asking. I want to know the IP address associated to www.example.com. That is how it originally works, the standard DNS. Now, what this protocol does, this new feature for query minimization, one, I have enabled query minimization, and it's part of what you will have to check, those of you who take part in the hackathon. When I enable in the authoritative, the Q&A minimization, this is a setup that we are going to enable at the authoritative server level. Instead of sending the full query, it only sends the authoritative server what that server needs to know out of the entire question to respond. If I am asking for the root, I am not going to send the full query. I want to know the IP address of etc. etc. If I have Q&A minimization enabled, what the recursive will do is ask the root authoritative server who manages .com. If I ask only that, instead of asking I want to know the IP address blah 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 blah, I will only ask what I need to know, who manages example.com, until I reach the server that has the response, and I will ask the full question to that one server. What is an advantage? Privacy. I'm not telling all the authoritative servers what is the query that I want to resolve, because it's information they don't need to respond. However, I'm given it. So I will not provide more information that I strictly need to resolve that query at the different levels. So that will enhance privacy in the sense that I am not revealing that information to all authoritative servers, what it is that I'm looking for online. Something that we didn't mention for DNSSEC and Q&A minimization is that nowadays all versions of all applications of recursive DNS servers, if you install from scratch and you don't do any changes to setup, by default, the recursive server will have the DNSSEC validation and the Q&A minimization feature with two different modalities, and those of you who take part in the hackathon will have more information on this. I think that by default they work in the more relaxed mode, not the most strict, because in some cases this could cause some sub-optimization aspects. It still works, but depending on which mode of Q&A minimization I implement, in some particular cases, it might take a bit longer to resolve that query. It'll take a bit longer to resolve a client's query. But again, Q&A minimization in a more relaxed mode and DNSSEC at the recursive server level are enabled by default, and the servers at the level of authoritative server for Q&A minimization, well, we don't need to do anything because it's an exclusive feature of the recursive, and DNSSEC, as Carlos said, needs to be enabled both ways. Authoritative has to have signed their zone, recursive enable validation, otherwise it will not work and won't be able to use DNSSEC. I will be able to resolve but not validate. And finally, this protocol is called hyperlocal. This feature is exclusive of recursive servers, and it will enable us. I mean, during the hackathon, one of the tasks will be to implement hyperlocal for the root zone. That setup, when I set up that hyperlocal feature at the recursive server level, that will cause that the recursive will download from servers that are available for that. So the entire root zone will download. And after a certain time, it will query it again because something might have changed in the root zone. I might have added, deleted, or changed something. So it will keep a full copy of the DNS root zone and the recursive server memory, in a way that the recursive server, when it needs to resolve a query, that first step of querying the root zone, what is the IP address of the authoritative DNS servers for the first level domain that I'm searching, is not needed, because it does have the memory of the entire root zone copy. So that first step can be skipped. It has the information from the memory, it will retrieve it and go directly to the second step, skipping the time that it would be needed to make that first query and wait for the response. That's something that we can implement. We can also implement hyperlocal. We can download it for authoritative servers that have that service enabled. I might be able to implement it if that service is enabled. I could implement it for every zone. I could preload any zone in my recursive server. Actually, some large operators or public operators do so for many zones, for the more widely used. Yes, this is a part, in a way, this is a CDN for a DNS. If we know that there's a number of queries or films and movies that are very popular, so you preload them because you know those queries will happen. We know that content will be queried a lot. So to wrap up the presentation, let me mention, well, of course, there are more protocols associated to DNS that we can implement to resolve these potential threats or problems in the different parts of the ecosystem. These 3 or 4 that we mentioned are just some. Maybe, or these are the more widely used or tested so far and the easiest to implement. And except DOH and DOT, these are the protocols that we will ask you to implement during the hackathon. Now, very quickly, let me present this program. This is an ICANN program that was launched a few years ago. It's a similar program to a program that was launched by the Internet Society a few years ago, and not of course, it just spans its own, the Manners program. So KINDS, it's sort of a similar program to Manners. Manners, if you're not familiar with that, Manners is originally an Internet Society program whose main purpose is to compile and promote best routing practices across network operators. KINDS is similar. We built on that great idea that Manners created, but this is a similar program for DNS. KINDS wants to be a repository, and we want to promote best practices on DNS server administration. Any DNS server, recursive, authoritative. So there's a site you can see on the slide, kindness.org, and you'll find many resources associated to that program, that set of good practices. And you'll find different setup examples of those main protocols that we mentioned before for the main implementation services, the recursive, authoritative servers. You'll find a self-assessment that you can take. That self-assessment tool needs to be done by technical experts that is closely linked to DNS server management, not just any person from the organization. So just someone that knows DNS servers, because of the type of questions that we have in that self-assessment. We don't compile that information. After you're done with the assessment, you can download a report. So based on the questions that you have in that self-assessment, the report will tell you, out of the best practices, out of this list of best practices and features that are considered as best practices by the internet community, you have implemented this and this and that, and you have not these others. And for the ones that you have not implemented, it'll provide links, information on what they are, and configuration examples. If you wanted to implement them, how to set them up in the most common software, both for recursive and authoritative servers management. You'll find best practices for all. So I encourage you to visit that site to do the self-assessment. If you finish the self-assessment and you don't download the report right away, you'll have to do the self-assessment again. It doesn't store information, so you might want to just download that report after you're done. Otherwise, you'll have to do it again. I mean, the self-assessment literally takes under 5 minutes. It's just under 7 questions. It asks whether you have implemented different protocols associated to the DNS. And you can also subscribe, become a part of the program, and you'll find all of the information that you need on that site. And that brings me to the end of our review. If you want to take part in the hackathon, here's the link again. You'll find a link that says registration form. You'll click there, you fill out your name and email address, and later on today we'll send you the information that you need for the hackathon that will take place this week. That would be all on my end. Thank you so much, and I encourage everyone to participate in the hackathon. It doesn't matter if you don't know anything about the DNS, if you've never managed DNS, or you might be familiar but you never managed recursive or authoritative servers, or any combination of such. The hackathon is a good option to start getting familiar with them. There will be a lot of people, not just Carlos and myself, a lot of people who are in this room right now, a lot of people who are not in the room right now, that are very knowledgeable. They know much more than we do about DNS. So even if you only cover 1 or 2 points of the entire list of tasks, well, you'll be able to set them up. You will be able to configure real DNS servers. It's not a simulation or servers that are online. You'll be able to query them. Of course, for security purposes, they are only enabled for queries within the lab for authoritative servers, but the two recursive servers that you are going to configure are recursive servers that are not public. You can only use them within the lab, but will be available for any DNS query in any internet domain on those servers. So please, I want to encourage everyone to participate. It's a good way to learn or to review, to learn for those of you who are not familiar with it, and to review some concepts for those of you who are. It will be fun. Don't worry. you will have the configuration files that we'll need to use, minor adaptations. There's a lot of help. Sometimes you just need to change the X with the number of the group that you were appointed. So if something breaks, don't worry. That is a good time to do it. It is maybe that is not a privilege that we will have in our workspace. In this case, if something doesn't work, nothing happens. The platform that Nico has developed in the past few years is great. There is a whole array of features, and it is very hard to have available at any lab. So this really is a great opportunity to practice DNS aspects that if you needed to set up scheme of this nature, it would be more difficult. We want to socialize the development of labs like this so you can actually all do it at home from the comfort of your own house. I think that would be all. Just one quick thing.
Comunidades que cualquiera que
One of the wonderful things of these communities is that whoever you ask, they will be helping you out if you wish. So please take advantage of that option. Nico's here. Hugo Salgado is here. He knows any amount about DNS. Hugo, please stand up so they see you. That's Hugo, our friend Hugo Salgado, who really is amazing what he knows about DNS in the region. And as I was saying, anyone here will be happy to help you out. We have a lot of activities throughout the year. You'll be seeing us around the entire week. And as you start moving around with the Discord, we can also be in contact with that. Now, let me show you this here. This is what you will see once you register with the form and once you get the links this afternoon. This is what the initial page looks like. You will each have a group assigned to you at the top left here. I'm GRP 51. That's my group, and I access with group 51. So each of you will receive this entire network. You'll be able to access everything. You'll be able to access these down here in green. One is DNS 1, DNS 2. These are the two authoritative public servers. The secondary ones, you'll be able to access the one that says SOA. You'll be configuring occult server, and also the secondary ones in S1 and S2. You'll be able to access Resolve 1, which is a recursive server that has pre-installed without any configuration at all. As the packet, it has a bind server installed. The Resolve 2 is another recursive server you have to set up, which has the unbound server from the recursive server, and that's it. Those are the servers that you will be able to access from all this that you have here. Maybe in the future, we'll be able to allow you to access a router and configure things such as Anycast and things such as those, but this is not something that we have implemented yet in this lab. But maybe for next time we will. Functionalities are in the lab, but we never did a lab with that, so we don't know what can happen, so we have to test this out first. So let's check this out for next time. We first have to check that. That could be the quote of the week. Test it out first. So we'll need to access, the only thing you'll need to access in your devices is a web browser. You can use it through a Mac device, through a Windows, Linux. You can access this through a Chromebook from a mobile device or tablet. About these last two, I cannot guarantee, but Windows, Linux, OS X, Apple, and any Chromebook, that will work. And with the rest, best of luck. Try this if you wish to do this in your mobile phone. But configuring things in a mobile phone is absolutely tedious and quite a headache. So once you can manage to access this, you will be able to follow the hackathon guide. And to access the service, you click on the server with the mouse. Don't do that, what I did here. You just click there, and a second window will open with the command line of the server. If this is SSH, all the servers This is SSH over HTTPS. So you don't need any SSH client. The browser will allow us to access this. And those of you who have a VPN with your company, with your organization, I recommend to take out the VPN. We need internet access with no firewalls or anything preventing HTTPS session with an SSH session inside. Sometimes we have had issues of people who cannot access it, and this is because they have a VPN and the traffic is being filtered. The outbound traffic is being filtered, so you get connected to the network of the hotel or the LACNIC's website. So once you get to this stage here, you have to change to the root administrator. You use the command su-, and then please don't download anything. You can download things, but we're all technical experts and we like to break things. And most of us don't like to read manuals. We start testing things, and until we really cannot go further, then you say, well, okay, I'll check with the manual. Manual is like the last resource we have. If we press on the red button, everything breaks down. Well, we should have done so, but we like to test things out before we consult the manual. Okay, so the browser is in the Amazon cloud. Don't download things or don't do any activities in the server that are not strictly related to this lab. Can you do this? Yes. But if we detect this, you will eliminate the service and you won't be able to continue with the laboratory. And doing that, we generate traffic and we also affect all the other participants. So the idea is to use this strictly for the functionality of this laboratory. So we make an appeal to your goodwill and best disposition. So this is like that, but you have full control over the servers. So thank you very much, and I hope you will all participate in the hackathon this week.
Están liberados.
Okay, that would be it. Let me remind you that you have to register until lunch. I don't know exactly until what time, but this form is available to fill out until noon. And this afternoon you'll be receiving the access credentials by email.